Let's look first at how we get the oxygen into our bloodstream and into the muscles where they use it. It's a multi-step process. First of all, oxygen is sucked into your lungs. When it's in your lungs, it diffuses across the membrane into your bloodstream. Then it's bound to hemoglobin molecules and it's carried around the body, going to the cells where it's needed, say in an arm muscle. It then diffuses into the cell. Once it's in the cell, it combusts. It's combined with some hydrocarbon to make energy and move your muscles. And then the waste products return the process. They diffuse back out, carried back, and the carbon dioxide diffuses back into the lungs and is breathed out. So there's a number of steps here. There's the circulation of the blood, but the most important and limiting step is the diffusion. The air has to diffuse into the lungs, into the cells, and back out again. So let's think a bit of what diffusion actually is. The basic idea of diffusion is that atoms move around. We saw that in the previous videos. So if you've got different sorts of atoms, like oxygen on one side, some of them will randomly move this way, and before long there'll be more spread out. So let's imagine, for example, that we are in a totally still air room. We measure the concentration of perfume, and we open a perfume bottle. Now when we open it, the air right by the mouth of the perfume bottle would have a high concentration, and everywhere else it'll be zero. No perfume in the air. But all the perfume molecules are going to be racing around. They might go this way, they might go that way. So after a while, some of them will be over here, some will be over there. So the distribution is going to look more like this. On average, they don't move one way or the other, but they just moving around. As time goes on, the distribution gets wider and wider and lower. So you have less perfume near the mouth of the bottle and more spread over a bigger and bigger region. Now we can estimate how fast this works. We've already calculated what the mean free path of the molecule is, how far it goes on average before colliding with something. Now you might think, if it goes a distance L between collisions, and there are n collisions in a unit time, the distance it would go would be about L times n. That would be the case if every time it goes the same way. So let's see, you had a molecule, its first motion was in this direction, its second motion was in this direction, its third motion was in that direction. But in practice, that's extremely unlikely. So there's a half chance of it going one way and a half chance of it going the other way. And the next time there's also a half chance, and the next time there's a half chance. The odds of all those half chances lining up in one direction or the other is extremely remote. In fact, in situations like this, the average distance you go is not L times n, it's approximately equal to L times the square root of n. And that is the standard deviation of this curve. Sigma is approximately equal to L root n. That's thinking in 1D. Of course, in reality it's 3D, which makes it a bit different, but this gives you a rough estimate of how far things are going. So as the number of steps gets larger, it does on average go up, but nothing like as fast as L times n. It doesn't go 10 times as far in 10 times the time. It actually goes root 10, so about 3 times as far in 10 times the time. And that's because it's a 2 steps forward, one backward type process. These things are pinging around at random. This is the same mathematics that's used to in calculating error propagation, which you'll see in the labs. So how far can molecules move? Now we saw that the mean free path of a molecule in air is about 10 to the minus 7 meters. Also we saw that each step was 10 to the minus 10 of a second, so n is around 10 to the 10 steps per second. So in 1 second it'll go a distance sigma roughly equal to L root n. It's approximately 10 to the minus 7 times root 10 to the 10, which is 1 centimeter, 10 to the minus 2 meters. So diffuses a centimetre in a second. That doesn't sound too bad. How about an hour? Well, an hour is 3,600 seconds, so n is now 3,600 times 10 to the 10. And the new sigma, with the new L, comes out as about 60 centimetres. Now that's not very big. Even after 10 hours, it's probably only gone a metre or two. So this is not how perfume spreads around a room. Diffusion is just too short-ranged. I know there are many experiments that you do at school which say it is due to diffusion, but the math just doesn't work out. In practice, even in what you think is still air in a room, there are a fair number of air currents and thermals and things, and that's usually what carries the perfume around. So the diffusion will carry out to a small region, and then air currents will do the rest. There is one interesting application of diffusion. It's actually what stops compost piles from stinking. In a compost pile, this is in your garden, you put piles of leaf and old vegetables and things like that down, and that gives you a network of air spaces between it. As these chemicals start decomposing, that generates heat, and the heat causes the air to rise, and it flows out through this network of spaces, and that sucks more air in at the bottom. So a well-designed compost pile, this is what's happening. But especially if the compost pile is pretty wet, you get a lot of spaces which are like dead ends. There's no easy way for the air to flow in and out of them. And in that case, the air inside these dead ends gets a bit stagnant, and all the oxygen is used up by the microbes, and you get anaerobic decomposition, which is what leads to smells. The thing that stops that is diffusion. Diffusion allows oxygen to get into these dead end spaces. So basically, you need the dead end spaces not to be much longer than a few centimetres in length, because that's this distance over which oxygen can diffuse in and stop it smelling. So a large part of good maintenance of compost piles is keeping the water level low so the spaces generally join up and aren't too big, so there's time for the oxygen to diffuse in and out, and that stops the smell. Okay, so that's diffusion. How does this factor into the limits on the human body?